species out of it, or you can get a worse species. For us, for the most part, I think nature's done a pretty good job of making things better as we've evolved from amoebas to fish to reptiles to mammals, apes, and then people. You know, but if all of this radiation were to have gotten down to the Earth's surface while those evolutionary processes were underway early on, billions of years ago, the amount of mutations would have been astronomically higher and probably would have led to chaos instead of the kind of organized evolution that we've seen life go through. So in some ways, not only does it protect us today, these two layers in the atmosphere, but they've also made it possible for life to evolve on Earth in the way it has. Stars. So what we've done is built all these satellites that we can launch into space where they're able to see all the other parts of the electromagnetic spectrum. And these are just 4 of them. Did I go through each of these yesterday? Tell you what they are? I mean, I'm not the kind of thing I would have on a test, but I just think it's interesting to know. The Spitzer is a space telescope that's been designed to look at the infrared portion of the electromagnetic spectrum. The SOHO telescope is actually a telescope, a space telescope that's designed to study the sun. And most of the sun's emissions are X-rays. Okay? So it's designed to focus, mainly on the X-ray portion and the ultraviolet portion of the light coming from the sun. The Chandra is an X-ray telescope, and it's focused mostly on distant stars. Some of the supernovae that we've tracked have been picked up by the Chandra telescope. And then the Planck telescope looks at the microwave energy. One of those famous pictures of the universe, and we'll get to it here, is called the cosmic microwave background. Have you ever heard of it or seen? It's the map of the universe, the energy that's left over, we think, from the Big Bang. And that map of the universe was developed by this telescope here. And if we didn't have these telescopes up in space looking out into the universe, we wouldn't have as much knowledge as we do. You might have a question.
No.
No? Okay. All right. So, and these are just 4 of dozens of telescopes that are in space giving us this kind of information all the time. Give you an idea of the light, but the infrared light is able to get through it. So we can actually see behind these dust and gas clouds by using infrared space telescopes. The optical telescopes, as I'll show you, and I have examples of all these, are the ones that are best at helping us pick out planets around other stars. The X-ray telescopes are able to give us a good understanding of what's going on in the corona of the sun and the coronas of other stars, and also giving us better understanding of what's going on in clusters of distant galaxies. And the gamma ray portion of the electromagnetic spectrum, the most energetic waves, are those waves that come from events like supernova and black holes. And even though black holes are black, you can't see the hole, they're still powerful jets of gamma radiation coming from. And we're able to detect those things by looking into different portions of the electromagnetic spectrum. So, portion. All of a sudden, we get a whole different picture. This is a plume of energy coming out of this radio galaxy. And it's showing, it's actually, if you were to overlay it, it's coming right from the center. So we think it's coming from probably a very active black hole in the middle of this galaxy. And when we look at these pictures, what scientists will do is they'll color the picture based on the wavelength. Okay, the radio waves are all different lengths. Each length of the radio wave is a different energy level. And so what they have here is the highest energy waves are colored in red, and then the lower energy waves are colored in blue and purple. it gives us an understanding of where the energy is concentrated and how the energy is flowing out into space.
Why is there yellow?
I'm sorry?
Why is there yellow?
Well, the yellow would be kind of a medium amount of energy, right in the middle. Yeah. Okay. So, yeah, I apologize. It has this in the, it takes me a while to get these uploaded to the Nearpod, but I found this picture the other day, and I was able to capture it over here. I just think it shows how much more we can see by looking at different portions of the electromagnetic spectrum. Our light energy.
Oh, light energy is responsive for
Yeah, mhm, sure. And what they are discrete little waves of energy. And what Max Planck discovered is that even though we may see the electromagnetic, like when you were looking through the prism, you saw like all the colors of the rainbow in the prism the other day, okay? What he found is that there's individual packets of energy that make up each and every one of those different color bands, okay? And that depending on the material that you're looking at, well, we saw the entire rainbow. There's some materials you might look at that only show certain bands and that are in different locations. There's a couple of green bars here, a couple of red bars, a couple of orange bars, a reddish orange bar. Those are the specific photons or wavelengths of energy that come from sodium atoms. And every atom in the periodic table has its own set of frequencies, which is why I refer to them as fingerprints, that we can use to identify which atoms are present. Yeah.
I have two questions. Yeah. One, why is there multiple different names for each of
Probably the most important chart that is out there in understanding the universe. It's called the Hertzsprung-Russell diagram. There were the two gentlemen that came up with the idea. And it's a plot of all the stars that they've been able to catalog in the universe. But they plot them in two different ways. On the vertical side, this is their luminosity or the brightness of the stars. And on the horizontal is the temperature of the stars. You can see the temperature really on top here. Okay, it gets a little complicated, but if you just think of it as that down here in the bottom right are the dimmest, coolest stars, and here in the upper left are the hottest, brightest stars. And what they found in looking at all the stars that they were able to get data on, looking at the amount of light coming from them and the temperature and the composition of the stars, that you get this pattern here where the stars are all sort of clumping together, gradually getting hotter and brighter as they go up along this path that we call the main sequence path. It's the path that most stars are following throughout their life cycle.